Hello everyone, so we can start. So this is the last slide I have presented now in the previous discussion. So we now proceed with our next topic. So we're done with the interpolation formulas. It's now time to introduce a new topic called polynomial approximations. So we have the first topic called linear approximation. So for linear approximation, this is a first degree polynomial approximation. no? So first degree polynomial approximation. So considering the graph of an actual function and the approximating function. No? So as you notice here, we have the function y equals f of x. So that is the actual function. No? Then we have the chord. The chord is the approximating function. Okay? So in other words, this actual function is approximated by a chord. No? So in this case, we have here f sub 0, and f sub 0 here is also the same as y sub 0. No? And also we have here, so f sub 0 equals to f of x sub 0. So that's the interpretation to that. No? Then f sub 1 is equals to y sub 1. Okay, that is equals to f of x sub 1. Okay, so then we have here x equals to x sub 0 plus rh. No? So you know this, I have introduced this before. So based from the graph, no? So we have here, this is x, no? This is x sub o, then this is rh. So to obtain x, we simply add x sub 0 and rh, no, to get x. So such that h is x sub 1 minus x sub 0 based from the graph. So we have h is simply x sub 1 minus x sub 0. Okay? So we know that this is x sub 1, right? This distance is x sub 1 and this distance is x sub 0. So x sub 1 minus x sub 0, that is simply h. Okay? And then we have r as a set, as is an element. R is an element of the set of real numbers. Okay? So meaning r here could be a decimal number or an integer. It could be since it is less than h, so we are expecting that r here between x sub 0 and x sub 1, okay, uh, is is a decimal number. So that is our expectation. It is a decimal number between x sub 0 and x sub 1. Okay, so we now proceed. So in this case, so when I talk about first degree polynomial approximation, okay, so n is equals to 1. So that's the interpretation to that. N is equals to 1. Okay? So a particular value of f between x sub 0 and x sub 1 can be linearly interpolated. No? So in other words, no, if I have here x sub 0, so this is x sub 0 and x sub 1. So this is the point for x sub 0, y sub 0, right? X sub 0, y sub 0, and this is the point x sub 1, y sub 1. Okay? So as you notice, this is the actual function and it is linearly interpolated, meaning we simply simplify it to be a straight line. No, instead it is a curve with this trajectory. So we have this chord, no, simply a line, no, connecting the 2 points. So that's the interpretation that it is linearly interpolated. So in other words, linear approximation to this curve. Okay, so there is a linear approximation. So the process of performing such is called linear interpolation. So the process of performing uh, the procedure, no, uh, in uh, in making it as a line, no, is called linear interpolation. No? So considering the first two terms of the Forward-Gregory-Newton interpolation formula, the linear interpolation formula is. So if we consider, we know that the Forward-Gregory-Newton interpolation formula makes use of delta, which is the first differences of a function, right? So in this case, we know that f of x is approximated by the Forward-Gregory-Newton interpolation formula, which is f sub o r delta f o plus r, okay, and so forth. No? So in that case, as you notice, when we stop here, okay, we stop here, it is now a linear function because we know that r is a variable that can be expressed in terms of x because there's a relationship between x and r wherein x equals to x sub 0, sorry. So this is the relationship, x equals to x sub 0 plus rh, right? So knowing that relationship, no, so r can be expressed in terms of x, where r is x minus x sub o over h. Okay, so that is, so and x is has an exponent of 1. Okay, that makes the whole equation to be linear. Okay, so that means n is 1. So that's the meaning of n equals to 1. Okay, so x to the first power, so meaning n is 1. Okay, so it's now a linear, it is a linear function now. So it is approximated by a linear function. This graph is approximated by a linear, it's by a line, no? Which is a linear function. Okay. So in this case, we have the equation f sub 0 r plus r delta f sub 0. So where r is called the real is called the real number, okay, which is the variable, okay. Instead of writing x, we write r, so the new variable, which is a real number, okay, real number variable, okay. H is the difference between consecutive tabular values of x, okay, or arguments denoted by the formula h equals x sub k plus 1 minus x sub k, such that k is an integer. K is an element of the set of all integers. Okay, so then we have delta f sub o. So the interpretation to this is the first forward difference of f with respect to x sub 0 and x sub 1. Because by formula, delta f sub 0 is f sub 1 minus f sub 0. I have already discussed this in my uh, previous video recordings, no? And This is f sub 1 minus f sub o. So this is the first forward difference of f, no, first forward difference of the function with respect to x sub 0 and x sub 1. Okay. Okay, so we can proceed. Next, we have here parabolic or quadratic approximation. So in my previous slide, I have discussed about linear approximation. This time is parabolic or quadratic approximation. So it's a second degree polynomial approximation. Okay. So considering the graph of an actual function and the approximating function. So this is the actual function, the blue curve, the red curve is the approximating function. Okay. So these are the 3 points. Okay, we consider. So this is x sub 0, f sub 0, x sub 1, f sub 1, and x sub 2, f sub 2. Okay? Now, the graph of the actual function passes through these 3 points. Likewise, the graph of the approximating function passes also through these 3 points. Okay? Applying the forward Gregory-Newton interpolation formula. No? So, in this case, we have f sub 0 equals to f of x sub 0, f sub 1 equals to f of x sub 1, f sub 2 equal to f of x sub 2. Likewise, x equals to x sub 0 plus rh. So in here, if we are interested in finding x, we simply add x sub 0 and rh. Okay? We simply add x sub 0 and rh. Okay? To get x. So and then we have here h is the difference between x sub 1 and x sub 0 or x sub 2 and x sub 1. So it is constant. It should be constant for us to, so that we can apply the forward Gregory-Newton, okay, interpolation formula. It should be constant, okay? So such that R is an element of the set of real numbers. Okay? So in here, since it is a second degree polynomial, n is equals to 2. The graph of f of x, okay, is approximated over two successive tabular intervals. So the graph of f of x, which is the actual function, okay? So the graph of f of x, which is the actual function, is approximated over two successive tabular intervals. So here are the tabular intervals, okay? The two successive tabular intervals, okay? So by a parabola of the form y equals ax squared plus bx plus c. So this is the graph of the parabola. It's quadratic, no? It is approximated by a quadratic equation, okay? Quadratic curve, okay? Chosen to pass through the 3 points x sub 0, f sub 0, x sub 1, f sub 1, and x sub 2, f sub 2, such that f sub 0 equals to f of x sub 0 equals to y sub 0, f sub 1 equals to f of x sub 1 equal to, okay, f of x sub 0 plus h, right? So we have x sub 1, we know that x sub 1 is x sub 0 plus h based from the graph, no? X sub 1 is equals to x sub 0 plus h, right? Based from the graph, that's the conversion. That's the transformation, I mean. Then, based from the graph also, f sub 2 equals to f of x sub 2 equals to f of xo plus 2h. So x sub 2, x sub 0 plus h plus h. What is that? X sub 0 plus 2h, right? X sub 2 is equals to x sub 0 plus h. That is equals to x sub 0 plus 2h. Okay? So that is equals to y sub 2. So a particular value of f between x sub 0 and x sub 2 can now be interpolated. No? So in here, since we are just approximating the actual function, no? So this is the approximation, which is a quadratic function. Okay? And with that, no, a particular value of the function that is not indicated in the problem. So these are the indicated points, right? How about this point? Okay, so we are to determine the value of f here using the equation y equals ax squared plus bx plus c. We are to determine the value of f, the value of the function. Okay, between x sub 0 and x sub 2. Okay, between x sub 0 and x sub 2. Okay, so knowing the equation of the graph, we can able to determine the value of the function at this point, at a certain value x, okay, between x sub 0 and x sub 2. So that's it. So the process of performing such is called parabolic or quadratic interpolation. Okay, so applying the forward Gregory Newton, okay, we can able to arrive with the parabolic equation or quadratic equation. Okay, so the process now of performing such, no, is called parabolic or quadratic interpolation. Okay, so considering the first three terms of the forward Gregory Newton interpolation formula, no, so we consider here the first three terms of the forward Gregory Newton interpolation formula. So the parabolic interpolation formula is now this. Okay? So up to delta squared f sub o only. Okay? Because our approximation is, it is a quadratic function. Okay? That's why up to delta squared f sub 0. So we have f sub o, r delta f sub o, r minus 1 over 2 factorial delta squared f sub 0. Okay? That's it. So it's so first degree, second degree, r squared minus r, right? That is r squared minus r. So what is the highest degree? Considering the first three terms, what is the highest degree? Highest degree is 2. Second degree. That's why it's quadratic. No? That's why the graph is a parabola. Okay? And of course, we are to convert r in terms of x using this relationship. X equals x sub 0 plus RH. Okay? So, that's it. So, knowing this quadratic interpolation, no, or parabolic interpolation formula. So, this is the parabolic interpolation formula now, where r equals to the real number, h is the difference between consecutive tabular values of x or arguments denoted by the formula. H equals to x sub k plus 1 minus x sub k, such that k is an element of Z. Okay? And then delta f sub O first forward difference of f with respect to x sub 0 and x sub 1, and is denoted by the formula delta f sub 0 equals to f sub 1 minus f sub 0. Delta squared f sub o is the second forward difference of f with respect to x sub 0, x sub 1, and x sub 2. It is denoted by the formula. So delta squared f sub 0 equals to e minus 1 squared f sub 0. Recall, how did it happen that delta squared becomes delta e minus 1 squared? I have already discussed this in my previous video recording that the delta equals to e minus 1. No? The operator delta in relation to the operator e. That is delta equals to e minus 1. No? Uppercase delta equals to e minus 1. That's why we can replace delta here by e minus 1. That's why we have now e minus 1 squared f sub o. And simplifying, expanding it, e squared minus 2e plus 1. No? You know how to expand this, right? So if I have a minus b squared, recalling algebra, that is a squared minus 2ab plus b squared. You know it, right? And then we distribute e squared. Okay. So f sub 0 is distributed, no, in every term of the group. Okay. So e squared f sub 0 minus 2e f sub 0 plus f sub 0. And also, recalling another formula, okay, the arc shift of the function, okay, is equals to f sub k plus r. So this is the formula I have introduced before. Okay, to get rid of e, okay, you add r to k. Okay, so if that's the case, e squared f sub 0 now will become what? So 0 plus 2. It becomes now f sub 2. How about e f sub 0? So e to the first power. So that is 0 plus 1. So it becomes f sub 1. That's why uh, this will now become f sub 2. Okay, right? This will now become f sub 2. 2f sub 1, right? Because e f sub o is f1. Okay, then f sub 0. Take note of this that f sub k, meaning is that is f of x sub k. Okay, f of x sub k. And in other words, the argument is shifted uh, rh. No? The argument is shifted by rh. So x sub k plus rh. Okay. So we have, so to get rid of r, we add rh to x sub k. No? So it is increased by rh. Now the argument is increased by rh. So we can now proceed. So here's the problem. We are to fit a polynomial in x of minimum degree to the following data. Okay. So solution by forward Gregory-Newton interpolation. Okay. So we are to analyze first if we can able to use the forward Gregory-Newton interpolation. So we have to analyze whether these are arranged in ascending order. Yes, they are. Okay. Next step, identify the tabular interval value. 0.5, no? 0.5, 0.5, and 0.5. Okay, so it is satisfied. We can now proceed with the next solution. So this will now be the representation. So 1 is equals to x sub 0, 3 is equals to x sub 4, and the likes. So you know that, so no need to elaborate. Then we construct the forward difference table. So okay, no need to discuss further this. We know how to construct it. Okay, so there. Next, so let's now apply the forward Gregory-Newton interpolation formula. So this is the formula for forward Gregory-Newton, right? Now at x sub 0 equals to 1, okay, so h is now, okay, let's go back. X sub 0, okay, correct. This is x sub 0, right? This is x sub 0, so equals to 1. So h is, okay, so I have already solved for the tabular interval value in the previous slide, that is 0.5, okay. And variable r is obtained as x minus 1 over 0.5, or simply that is 2x minus 2. If we simplify that using algebra, that is 2x minus 2. Okay? So 1 over 0.5 is 2. That's why we have 2x. 1 over 0.5 is 2, right? That's why it's minus 2. You know that, so no need to elaborate. So then f of x is approximately equal to 2 plus, so this is found in the table, right? F sub 0 is found in the table. So we have 2. There, f sub 0, this is f sub 0. This is delta f sub 0, right? Delta squared f sub 0. Delta cube f sub 0. Delta to the fourth f sub 0. So we will use all of those. Okay. Okay. So we have delta f sub 0, delta squared f sub 0, delta cube f sub 0, delta to the fourth f sub 0. And nothing follows because the limitation is up to delta to the fourth f sub 0. Okay. So in that case, we just substitute, no? And we will arrive with this solution. So r is 2x minus 2, okay, 2x minus 2. 2x minus 2 minus 1, that is 2x minus 3. 2x minus 2 minus 2, that is 2x minus 4, and so forth. So as you notice, this is already eliminated, delta to the fourth f sub 0, because this is 0 based from the table, no? So based from the table, it is 0. It so happened that it is 0. Therefore, there's no chance that it will be a 4-degree polynomial. So instead, it will now become third-degree polynomial because delta to the fourth f sub k is equals to 0. Okay, so we now proceed. So this is now the simplification. So you know how to simplify. No need to explain in detail, right? You know how to perform algebra, right? So I, I don't think I need to explain it in detail, no? So you know it, no need to explain in detail. and we'll arrive with this answer: x cubed minus 2x plus 3, which is a third degree polynomial. So we satisfy the condition. Okay, we satisfy the problem. So fit a polynomial. So it is a third degree polynomial. Polynomial in x of minimum degree. Okay, to the following data. So minimum degree. So the fourth degree, it's not a fourth degree polynomial because it is 0x to the fourth, right? Because the fourth differences of the function is 0. That's why, okay, that's why it becomes now third degree. So that is based from the computation. It's now third degree. So fit a polynomial in x of minimum degree to the following data. So we had satisfied the problem. So this is now the answer. Okay? So I hope you get it. Alright, so that's all for today. Good day, everyone.